Hello and welcome to the fifth series of lectures on Math 232, Real Analysis. So first, let us recall what we have discussed in the previous lecture. So we have first considered the elementary content space in Rn. So this consists of the following triple. So our ambient space is Rn, the set of n tuples of real numbers. In is the semi ring of cells, half open, half closed cells. And kappa n is what we call the elementary content. And the elementary content of a cell is defined in this way. So it's basically the product of the endpoints of your cell. So for instance, in this case, A has the components A1 up to AN, where n here is the dimension, and B has the components B1 up to Bn. So you take the difference of the corresponding coordinates or components, take the product, and that would be your elementary content. So for instance, in the two-dimensional case, a generic cell would look like this. So the content would be basically the area of this cell. So from this elementary content space defined on the semi-ring of cells, we can apply the Hans theorem to extend this into the ring generated by the cells. And we denoted this by Fn, the set of figures last time. Okay, so, well, basically the definition or the extension is via taking the sum of the cells that comprise the figures. So recall that the figure, let's say in R2, is basically the pairwise disjoint union of cells. So for instance, you have this figure here. Okay, and of course that should be corrected. Half open, half closed. So here the bottom will not be included. So you just take the content of those components. Based on this elementary content space, we can construct the so-called Handcolmogorov extension. And this Handcolmogorov extension is what we call the Lebesgue-Borel measure space. And it has the following three components. So again, Rn as your ambient space. And Brn is the Borel sets. So this is the sigma algebra generated by the open sets. And note that this can be generated as well by the cells and of course by the figures. And the last component is the Lebesgue-Borel measure. So this Lebesgue-Borel measure lambda n. So it's defined on Borel sets with values in 0 to infinity. And this is basically the restriction of your outer measure to the Borel sets. So in other words, if lambda n star is the outer measure, then restricting this outer measure to the Borel sets is your Lebesgue-Borel measure. And indeed, we have shown that this is indeed a measure. So if the Lebesgue-Borel measure is just the restriction of the Lebesgue outer measure, then it can be calculated or computed in this way. So if you have a Borel set A in Rn, you cover this by cells, countable collection of cells, C sub k, k from 1 to infinity. You take the content of each cell, and then take the series or the infinite sum. And then among all this possible infinite sum, you take the greatest lower bound. Okay. So this is basically the definition of the Lebesgue outer measure. But since the Lebesgue outer measure coincides with the Lebesgue-Borel measure in the case of Borel sets, then this should follow. Well, the construction of Handcolmogorov extension is in fact the restriction of the Caratodori extension. So here we have another measure space, and in fact a larger measure space, the Lebesgue measure space having the components Rn, your ambient space. Here, sigma lambda n star is the collection of Lebesgue measurable sets. And recall that a subset of Rn is Lebesgue measurable with respect to the Lebesgue outer measure if and only if, let's say, for any subset E of Rn, if we take the outer measure of this set, it must be the sum of the outer measure of elements in E that are in A plus the outer measure of the set consisting of elements in E that are not in A. So this is a measurability in the Caratodori sense. And as I said, this is a larger measure space since we know that Borel sets are Lebesgue measurable. And this Lebesgue measure here will be denoted by lambda n as well. So again, to summarize, starting from the elementary content space on cells, you apply Hans' theorem to extend this on the rings of figures. You construct the outer measure from the corresponding pre-measure. And you restrict the outer measure to the Lebesgue measurable sets to obtain the Lebesgue measure space. A further restriction of this measure space to the Borel sets will be the Lebesgue-Borel measure space. Now, if we want to emphasize the difference between we want to distinguish the Lebesgue-Borel measure and the Lebesgue measure, we denote the Lebesgue-Borel measure by lambda n LB and the Lebesgue measure by lambda n L. So the subscripts tells us what kind of measure are we dealing with. So LB for the Lebesgue-Borel measure and L for the Lebesgue measure. However, if it is clear in the context, since the Lebesgue-Borel measure is just the restriction of the Lebesgue measure, and if we do not distinguish the two measures, we use this abuse of notation, wherein we remove the indices. Okay, having said that all Borel sets are measurable, are all Lebesgue measurable sets Borel? Well, this set of inequalities tell us that this is not the case. So the first inclusion here, the first strict inclusion here, tells us that there are Lebesgue measurable sets that are not Borel sets. And an example can be provided by via the Cantor set and the Cantor function, which is similar to what they call the Devil staircase function. So you can look at that if you want to know Cantor sets and Cantor functions. And we will not go into the details with this construction. You can look at the references of our course notes for the Cantor sets and the Cantor functions. Now, this second inclusion here, strict inclusion here tells us that not all subsets of Rn are Lebesgue measurable. In other words, there are non-measurable subsets of Rn. And an example can be provided via the action of choice. So again, if you are interested in the construction of a non-Lebesgue measurable set, then you can consult our course notes, specifically in the appendix. So the action of choice tells us that suppose you have a collection of non-empty sets that are pairwise disjoint. You have a set that consists precisely one element in the collection. So in other words, and roughly speaking, you can pick or you can choose one element from the pairwise disjoint collection of non-empty sets. Okay, having said that not all Lebesgue measurable sets are Borel, it is still interesting to see if there is a connection between Borel sets and Lebesgue measurable sets in Rn. Is there a relation between such sets? Can we relate the two? Well, to answer this question here, we need to consider another concept of measures, inner measures, and relate this to the concept of outer measures that we have already discussed. And after that, we discuss how to complete measure spaces. So what do we mean by a complete measure space? And we will discuss this in the succeeding lectures.